Dear students, I hope that you would be doing good. With lecture 13, we actually completed chapter 3 of our textbook, and now we are moving towards chapter 4, which is a new topic. Chapter 4 is related to fluid kinematics. So we'll study chapter 4 today. Kinematics is the study of motion without regard to the cause of the motion. Before moving further, I would like to describe continuum hypothesis or continuum approach, or that can also be called as macroscopic approach. In continuum approach, we assume the system to be a continuous form of matter. So we say that we study average properties that are evaluated over a small volume containing a large number of molecules so that we can neglect the spaces between the molecules, and the properties that we measure, they are assumed to be continuous throughout this fluid. So that is what we call continuum hypothesis. To study the motion of fluid, we have two approaches. One approach is called the Eulerian approach, and there is another approach which we call the Lagrangian approach. So in a Eulerian approach, the properties of or of a fluid, or any property of a fluid, is function of time and space. So we say, for example, temperature T is a function of x, y, z, and time. In contrast to that, in Lagrangian approach, we follow individual fluid particles as they move about, and we measure the change in their properties. So in a Lagrangian approach, a property is not a function of x, y, z or space, but rather it's a function of time. It's just like we are tagging a fluid particle.
So in figure on your screen, you can see smoke coming out of chimney. The lines coming out of chimney show the path taken by smoke particles. We assume a fixed position O, and we write temperature at position O T is equal to T as a function of x naught, y naught, and time. If we have many such locations like O, we can define the temperature of the whole field as T is equal to T, X, Y, Z, and T. That was Eulerian approach. In contrast to that, in the Lagrangian approach, we actually don't try to find out the temperature as a function of position. We actually tag a particle, or you can say that we, as shown in the figure, we would probably attach a temperature measuring device to fluid particle A, and then we'll have temperature TA as a function of time. If we use many of these temperature measuring devices with a lot of particles, we'll probably have the temperature of the whole field. We will not know temperature at a specific position unless we don't know the position of the particles as a function of time. If we have sufficient information available, we can convert the Eulerian approach to Lagrangian approach, or the Lagrangian approach to Eulerian approach.
So moving on, we will also study streamlines, pathlines, and streaklines. Streamline, we already had an introduction with the streamline. A streamline is a line which is tangent to the velocity vector everywhere. An equation of streamline is given as dy over dx is equal to v over u. The figure that is now come on your screen explains why we have this equation dy over dx is equal to v over u. So a path line is the locus of points traversed by a given particle as it travels in the flow field. So a single point, so that's Simply speaking, pathline, you can think about pathline as being trajectory of a fluid particle, because it's the locus of points traversed by a given particle as it travels in the flow field. So, and the streak line. Uh, Streakline is an instantaneous line whose points are occupied by all particles originating from some specific point in the flow field. So we- how we draw a streak line is we say, okay, we choose one location and we see which particles are going through this point, and then we say, okay, at time t is equal to t1, all the particles that have previously flowed or passed through this point, we want to see where they are and make a line joining all these particles. So the line that we make by joining all these particles, that is a streak line, and all these particles have passed through some specific location. So streamlines, path lines, and streak lines are all different lines. They are same only in one situation. When we have a steady flow field, all these lines are same lines. So now we see a problem as an example, that is problem 4.11. The statement says a velocity field is given by v is equal to xi hat plus x into x minus 1 into y plus 1 j hat, where u and v are in feet per second and x and y are in feet as well. Plot the streamline that passes through x is equal to 0 and y is equal to 0. Compare this streamline with the streak line through the origin. So what we say is we want to plot a streamline that goes through the origin. The velocity field v is given as you can see on your screen. We know that the u velocity u is equal to x and v is equal to x into x minus 1 into y plus 1. So and we also know the equation of streamline, that is dy over dx is equal to v over u. So we use the equation of streamline dy over dx is equal to v over u, and we put in the values of v and u that we that are given to us in the problem, and then we separate the variables and integrate the equation, and this gives us the equation of all the streamlines of this flow field that is given to us. The equation is given as ln on natural log of y plus 1 is equal to x square over 2 minus x plus c. This is the equation of the streamline. Now we will go on and try to find out the equation of the streamline that passes through the origin. So we still don't know the value of constant c, but we want to find out equation of streamline that passes through the origin. So we said that in the previous equation, that is the general equation of any streamline, we said if x is equal to 0 and y is equal to 0, the constant c comes out to be 0. So we have a new equation for a streamline that passes through the origin, and that is given as ln of y plus 1 is equal to x square over 2 minus x. We rearrange it, and the final form of equation that we have, you can see that on your screen as well, that is y is equal to e raised to the power x square over 2 minus x and then minus 1. This streamline is also plotted on your screens. You can see that the streamline passes through x is equal to 0 and y is equal to 0, and it has a maximum at x or minima at x is equal to 1, and then it passes through x is equal to 2 and y is equal to 0.